SwayamPrabha. Digital India. Educated India.
Hello everyone. So we were discussing in the last class about deriving the Smegrinsky coefficient, and we derived it to be 0.17, as you can see in the slides. We realized that as we derived it, we found that LS, the mixing length, scaled with delta, and so did the filtered rate of strain, so did the eddy viscosity, and so did the residual stress tensor, the anisotropic part of the residual stress tensor. All of that scaled with delta. So we knew that, right? Now we have proved it mathematically. We found out that CS would be approximately equal to 0.17. So now that the Smegrinsky model has been defined, so with the specification of the Smegrinsky length scale, LS, the LES equations can now be closed and they can be solved to determine the filtered velocity field U bar. Now you can do this without an explicit specification of the filter, because what happens is the filter appears in the LES equations. Okay, the filter, the filter neither appears in the LES equations nor in the Smegrinsky model, right? The delta, you do not see where the delta is appearing, right? So all you have is nu r is equal to LS squared times S bar, and you are saying that it is scaling with delta. Okay, so that filter, we don't have a filter that is appearing explicitly in the LES equations or not. I'm not talking about the filter width, I'm talking about the filter itself, right? So it is, it's sort of an implicit filter in the sense. You don't have an explicit specification of the filter. So for homogeneous isotropic turbulence, there is an implicit filter, unique implied filter, which is the Smegrinsky filter, for which the calculated spectra are consistent. So let's say the isotropic for isotropic turbulence, it is suppose that for isotropic turbulence computed using DNS. Okay, now what happens is you get an energy spectra given by E kappa, and say the same flow is computed using LES, and it yields a filtered energy spectrum E bar of kappa. Okay. So now what happens, if you relate the two, E bar of kappa and E of kappa, and take a square root of it, you should get the transfer function, isn't it? So the transfer function is defined as follows, which is E bar of kappa times E of kappa. Because remember, if you remember earlier, E bar of the filtered spectrum is defined as G of kappa squared times E of kappa. Why is it squared? Because kinetic energy is square of the velocity. Because of that, the filter function appears, two times, as in squared. So then when you want to calculate the transfer function, it's basically the ratio of E bar of kappa filtered spectrum to the original spectrum from the DNS and the square root of that. So this is the transfer function for the Smegrinsky filter, right? Only with this filter does the filtered DNS velocity have the same field as the filtered velocity field obtained from LES. While with this filter, the Smegrinsky model produces the correct spectrum. There is no implication, right, that other statistics might match. All we are saying is that the spectrum matches up until the cutoff wave number. That's what we are saying. So the Smegrinsky filter, you can estimate it for high Reynolds number turbulence, and for LS smaller than the integral length scale, so basically LS much less than L11 or LS over L11 much less than 1, all you need to do this by estimating E of kappa and E bar of kappa, you can get what the filter is. Because remember, that is what we are saying. This G hat of kappa never appears in the equations. You can get that by estimating the filtered spectrum and by estimating the actual spectrum obtained from DNS. If you use those two, you can get the filter. But otherwise, the filter does not appear explicitly. I'm not talking about a filter width. I'm talking about a filter G of kappa. Okay. Now for E of kappa, so let's see how that exercise works, right? So for E of kappa, let's say you have this model spectrum and you use the Powers form, as in the Powers form of the filter, where you have this exponential minus 3/2 C of kappa eta to the 4/3. So if you had the other kind of spectrum used the value of beta, but the power spectrum uses this function here. Now, in order to estimate E bar of kappa, all you need to do is the characteristic filtered rate of strain is approximated by S bar squared to the half, and then your LES momentum equation becomes this. This looks very similar to what we had in the Reynolds equations, where we group the eddy viscosity and the kinematic viscosity together. We are doing the same thing here. The eddy viscosity and the kinematic viscosity are grouped together. That is your diffusion term, viscous diffusion term, and then you have the pressure term and this, obviously the inertial term on the right hand side. So again, like this, we are making the same argument as we made earlier. This is identical to the Navier-Stokes equations except for this coefficient nu plus nu r. Okay, so basically this gives you the same solution as the DNS, except now your Reynolds number is lower by a factor of 1 plus nu r over nu. So what we are trying to say is your apparent Reynolds number has now reduced in LES. That's it. Otherwise you are doing a DNS. You are essentially doing a DNS at a lower Reynolds number. So that is what you have. So you have reduced the Reynolds number of the DNS calculation. So you are, and then, so it is essentially the same as the Navier-Stokes equations. So the solution is same as the DNS, except the Reynolds number is lower by a factor of 1 plus nu r over nu. So now if you calculate your effective Kolmogorov scale, according to the Kolmogorov relationships, it is nu cube over epsilon to the 1/4. And that's what you're doing here. Nu plus nu r, the whole cube over epsilon to the 1/4. So you get this ratio and it is a function of LS. And then provided that this eta bar or this apparent Kolmogorov scale is very small compared with the integral length scale, it is consistent to suppose that the LES yields a spectrum, this one, right? So your LES spectrum will now be with eta bar, as you can see here, not with eta, whereas with eta bar, as you see here, and eta bar is the apparent Kolmogorov scale as modeled in LES. So this corresponds to the power filter defined earlier with the filter width of delta equals LS over CS. So CS is this expression here, which is equal to, which is approximately equal to 0.15 after substituting the value of C, pi and all that, you get it to be 0.15, 1 plus 7 eta over delta to the 4/3, the whole thing to the 1/4. So now your CS value is slightly different, right? So the important point is that there is a unique filter given by the above equation. The particular filter deduced is an approximation because what we did is we neglected the fluctuations in S bar, right? We made this approximation of assuming this Megrinsky model S bar is approximated by S bar squared, the whole thing to the square root. So because of that, we neglected some fluctuations. But otherwise, it depends on the form assumed for the dissipation spectrum, as in for the power spectrum, right? Power spectrum is what we had defined. So what is shown here on the left hand side are basically filter transfer functions, G hat of kappa for a Gaussian, a Cauchy filter, a power filter, all implied by the model spectrum. Okay, and then the filter functions on the right hand side are the Gaussian, Cauchy power implied by the model spectrum, and that is the dotted line. Okay, so what I have here is delta G of R. This is in physical space, this is in spectral space. So it's the same thing, right? So we have here the G hat of kappa derived from the actual spectrum and from the filtered spectrum. Again, this is not from experimental data, this is just taking the model spectrum. So if you calculate, so E bar is this function here and E is this function here. So you calculate G of kappa by just taking E bar of kappa divided by E of kappa to the square root, and you get a transfer function, which is what is plotted here. So the power spectrum leads to the power filter, whereas the exponential spectrum leads to the Cauchy filter, and the model spectrum leads to the filter given by this. So this model spectrum provides the most accurate representation of the dissipation spectrum, and so the filter deduced from it is the best estimate for the Smagrinsky filter. So this one is your best estimate for the Smagrinsky filter. So earlier we had derived the Smagrinsky model, here we have the Smagrinsky filter. Now let's look at the limiting behaviors. So an ideal application for LES is to use high Reynolds number turbulent flow with the filter in the inertial subrange. But that is ideally what you want to do. But what happens if you have a very small filter width? If the filter is in the far dissipation range, as in if it is very small, then your Smagrinsky coefficient turns out it would be about 0.13, somewhat lower than the 0.17 that we estimated if it was in the inertial subrange. Also, the Smagrinsky model in that case would yield nu r approximately scaling with delta squared in the far dissipation range, a much more rapid decrease with delta than the delta to the fourth third that is what you have in the inertial subrange. So from a practical viewpoint, this uncertainty in this limiting behavior is not a major concern, since what happens is for very small delta over eta, meaning delta over eta, that ratio, if that keeps reducing, what happens is the viscous stress dominates over the residual stresses. That's it. So it's not a major problem. You just approach more and more DNS. The question though is that is not really required, because the whole idea of using LES is to save on computational resources. If you have a small filter width, you are getting closer and closer to DNS, then you might as well do a DNS. You understand what I mean? But it is not of a major concern to us. What is more concerning is the large filter width. So the opposite extreme of the filter width being very large compared to the turbulent integral length scale is that in the limit that delta L tends to infinity, as in delta over L tends to infinity, it becomes very large. What happens is U bar tends to be more approaching U average, the mean velocity, because you're not modeling any scales at that, you're not resolving any scales at that point. You get to a point, you are tending to a point where you're not resolving any scales anymore, so you are approaching a RANS. So the residual velocity u prime approaches the fluctuation u of x of t. That is what we used in the Reynolds equations. And finally, the residual stress tensor basically tends to the Reynolds stress tensor. That is your two extremes of the limitation in terms of the filter width. Another limitation is, what if this is applied to a laminar flow? So for laminar flow, the Reynolds equations essentially revert to the Navier-Stokes equations, and the Reynolds stresses are 0. On the other hand, in LES, the residual stress remains non-zero in laminar flow. Because for instance, for laminar shear flows, the residual stresses are 0 and the appropriate value of Smagrinsky coefficient is CS is equal to 0. Whereas a non-zero value of CS would lead to incorrectly estimate the residual shear stresses to be non-zero. Okay? And consequently, the Smagrinsky model with a constant non-zero value of CS is incorrect for laminar flow. So that's one limitation. Now, this would all be alleviated if you use a dynamic version of the Smagrinsky model, because CS squared is calculated dynamically based on certain equations. And most likely CS squared would be equal to 0 in a laminar flow. When you apply CS is equal to 0.17, that is never the case, right? Some additional discussion about near wall resolution. So in LES, there are two ways to treat near wall regions. One is this actually resolving the gradients near the wall. So we call that near wall resolution, or NWR. And in this case, the filter and grid are sufficiently fine to resolve 80% of the energy everywhere, including the viscous wall region, whereas the LES with near wall modeling, we call that NWM, the near wall motions are not resolved but instead are modeled. So in LES NWR, in order to resolve the near wall motions, the filter width and grid spacing are such that the number of grid nodes required would be of the order of, it would scale as RE to the 1.76. So because of that, NWR becomes nearly infeasible at high Reynolds number flows. Okay. On the other hand, for NWM, since near wall motions are modeled, that is more practical. Computational requirements are not that stringent, so it can be done. It is more practical. There are two ways in which we can test the LES model performance. One is a priori and the other one is a posteriori. And a priori testing is probably not something that you regularly see, but it's still available out there, and there are several studies that do that. So an a priori test, what it does is it uses experimental or DNS data to measure directly the accuracy of the modeling assumption. Okay, how does it do it? For example, the relation for the residual stress tensor given by the Smigrinsky model. It basically takes that directly. It estimates the residual stress tensor from the DNS data and tries to estimate, okay, how accurate is it? In the a posteriori test, that's pretty straightforward. You actually do an LES calculation, okay, and what you do is the accuracy of the LES model is assessed by comparing filtered velocity average or Reynolds stresses, and it is compared to experimental or DNS data that is out there. So you compare statistics to DNS data, statistics from DNS data or statistics from experimental data. So it is appropriate to perform a priori test to assess directly the validity and accuracy of your approximation. And typically when a new model is developed, this is one of the first tests they do in order to assess how good is your approximation of the subgrid scale stress, of the residual stress. Okay, but eventually you will need to do an a posteriori test to see how effective your LES model is. So the a priori test basically uses the residual stress from the DNS data. So this is an example. So Clark et al. In 1979 did some a priori tests, and this is what they did. They took a 64 cube DNS data with an RE lambda of 38. They extracted the filtered velocity field and predicted the Smigrinsky residual stresses, so tau IJR, right, anisotropic part of the residual stress tensor. They obtained that from the filtered field. They then compared it with the residual stresses of the DNS field. Okay, so they took the filtered velocity and based on the Smigrinsky model calculated the residual stresses. So LS squared, CS times delta, that squared multiplied by S bar, and they get the residual stress tensor, isn't it? That is based on the Smigrinsky model. You can also calculate the residual stresses directly from DNS data, and they compared two to see how good is the Smigrinsky model. That is an a priori testing. A posteriori testing, what you do is you calculate the U bar average, right? You calculate Rij residual, and then you compare it to the U bar average in UI Uj, the Reynolds stresses from the experiments of DNS. Remember, these two are not directly equivalent, but what you're doing is as you reduce the filter width, these two will turn out to be more and more equivalent. So what you're doing is you're comparing the U bar average, because you have to compare statistics. You are running instantaneous, you're running unsteady equations. You have to only compare statistics. Every realization is different between turbulent flows. So you have to compare statistics. Now for inhomogeneous flows, the general conclusion from a posteriori is that the Smigrinsky model is too dissipative because it transfers too much energy to the residual motions. And so essentially it is solving, using the Smigrinsky model, the LES equations are solving a much lower Reynolds number than is actually than the one that we are actually trying to model. Okay, so for example, if you're trying to model a 1 million Reynolds number, LES is calculating for the apparent Reynolds number is it could be as low as, say, just putting out some number out there, as low as 30,000, for example. So then it is the difference is much larger. So that shows that the dissipation is too much with using the Smigrinsky model. So now moving on to LES in wave number space. So we saw this where we used DNS in wave number space and we looked at the velocity being converted into Fourier space using the Fourier series, right? So you have this U of xt, which is the summation of e to the I kappa dot x u hat, and u hat is this Fourier mode, and we have it like this, right? This is how it was defined. So the Fourier coefficients satisfy the conjugate symmetry, and they are also orthogonal to kappa. Right? Kappa naught, which is 2 pi over L, is the smallest resolved wave number. Okay, now for a sharp spectral filter, your U bar hat is essentially the Heaviside function. The sharp spectral filter in wave number space is the Heaviside function multiplied by the U hat, isn't it? You take your DNS field and you multiply it by the Heaviside function, you essentially get your filtered velocity field in wave number space. So now if you write your Fourier series of the filtered velocity field, it looks like this. U bar of xt is e to the I kappa dot x, U bar hat of kappa comma t. Or in other words, it is summation. Now the summation is only till kappa c, and you have e to the I kappa dot x, U hat of kappa comma t. Isn't it? That becomes your filtered velocity field. So this is how the filtered velocity field is defined in terms of the Fourier series. Now your summation is only till kappa c, not for the entire kappa, isn't it? We have seen this before. And we define our cutoff wave number as half n kappa naught because that is our new wave number. This is your LES grid, and since the filter is taken to be isotropic, the second summation term, basically the last equation in the previous slide, is restricted to wave numbers within a sphere of radius kappa c. We have seen this multiple times. All which is within a cube of side 2 kappa c. If you remember, your cube is like this, right? I'm showing it as 2D, and you only take until a radius of kappa c, because remember LES stops at kappa c. Okay, kappa c is the radius, so essentially you have a sphere with a diameter 2 kappa c, right? And you stop here. Everything here we ignore it, isn't it? A sphere within a cube. And LES, it's the same thing, except now the sphere in LES has a diameter 2 kappa c. Okay, so the fraction of represented coefficients of the filtered velocity field in wave number space that are non-zero is basically 4/3 pi kappa c cube, which is the radius of the sphere, divided by 2 kappa c cube, isn't it? 2 kappa c cube becomes the total number of wave numbers in the cube, right? Whereas 4/3 pi kappa c cube is the total number of wave numbers in the sphere. So the ratio of this gives you pi by 6. Okay, so that is the fraction of represented coefficients. And then you have your Navier-Stokes equations in wave number space. This is actually what you would write for DNS. We know that this is basically a set of ODEs, right, that can be algebraically solved. And in the filtered space, this is what it looks like: d dt of uj bar plus nu kappa squared uj hat, right, nu j bar hat. And then you have this projection tensor, but now instead of the filtered velocity field, we are putting the Heaviside function in there. So essentially you have, pi by 6 n cube set of ODEs which you can solve. The closure problem arises because of the nonlinear term, and then it includes unknown Fourier coefficients, namely for everything that is greater than kappa c. That is the residual fields, right? For everything greater than kappa c, you don't know what these values are like. Okay, so that is where the LES equations come in and you solve for that. Closure is achieved. So that is for full closure, we are just providing the LES equations in wave number space. But I want to end these notes by discussing a little bit about the statistical view of LES. So some plots are given here. I'll come to this in a second. The question we need to ask yourself is, what is the ideal LES model for the residual motions? Right? What is the ideal LES model for residual stresses or wave number space? So in Rand's turbulence models, the above question is quite easy to answer. For instance, the turbulence model that gives us the right Reynolds stress field is the ideal LES model. But let's consider an accurate DNS of homogeneous isotropic turbulence. We use a pseudospectral method. We use n DNS cube number of modes. Now, if you consider LES of the same flow, our cutoff wave number is kappa c, right? So the number of represented modes, it would be NLES cube, right? NLES cube. So NDNS cube and NLES cube. Obviously, NLES is less than NDNS. Now, what happens is, as is often done in practice, the initial conditions in DNS are set by specifying Fourier amplitudes deterministically to obtain the specified spectrum, while the Fourier phases are set in random. This is what you typically do, especially when you're using a pseudospectral method. The amplitudes are obtained from DNS, whereas the phases are set in random. So if you consider different realizations in which the initial conditions are identical for kappa less than kappa c but different for kappa greater than kappa c, then what happens is the initial states in the DNS evolution case differ because of the different phases, and consequently their paths are different. Look at this. So this is DNS, and as you can see, because the phases are different, their initial conditions are also different because the phases are set in random. Even though the amplitudes are the same, because the phases are set in random, the initial conditions are different, and also because the initial conditions are different, they have different paths. So this is each and every realization basically. Essentially, how many curves are there? About 5 curves. Essentially, you have done the same DNS 5 times. But each time you do it, the initial conditions have random Fourier phases. So because of that, you are getting different initial conditions and you are also proceeding along multiple paths. That is what we are trying to say. The filtered DNS, on the other hand, are basically projections of the DNS sample paths onto a smaller LES grid basically, or state space. So the initial states are identical by construction. Why? Because you are only taking the amplitude. But as time evolves, because of the nature of turbulence, it is proceeding along different paths. By the time you filtered this out, right, those random Fourier phases just went away. The fact that the amplitudes were the same, so you got the same initial condition. However, they still proceeded along multiple paths, different paths, because every realization in turbulent flow is different, even if you start with the identical initial condition. Right? So for a deterministic LES model, there is a unique evolution of the state from the given initial condition. You start from the same initial condition, then you get exactly one solution, even if you proceed along even if you conduct it multiple times, isn't it? And for a stochastic LES model, so that is more like a random type of a random process based LES model. You have slightly different initial conditions and they proceed along multiple paths, different paths as well. So here we have states of different realizations that disperse, but the cause of the dispersion is just very different than what you would have in a filtered DNS field. So the conclusion here is that the filtered DNS fields are not uniquely determined by the filtered initial condition. As you saw, they started from the same initial condition, okay, but still they proceeded along different paths. Second, it's impossible to construct an LES model that produces a filtered velocity field that matches exactly those with the DNS realization by realization. You just cannot do that. The best that can be achieved is a statistical correspondence between DNS and LES filtered fields. Okay, so that is the conclusion we obtained from that discussion related to this statistical view of LES. Okay, and this plot pretty much summarizes that. So this completes the notes required, the modules required for this class. We have now completed all the modules. What we will do in the next class onwards is we will try to work out some problems. We'll try to work out as many problems as possible in order to give you some practice in looking at some derivations, looking at some very simple filtered functions, how those can be derived, averaging procedures, looking at how we can assess Reynolds stresses, and so on. We'll try to work out multiple problems. Thank you.